Now, finally, we're going to go ahead and see how we can predict the pH, the acidity or basicity of different solutions of things that don't on the surface look like acids or bases. And what I'm talking about are salts, ionic compounds that are formed when an acid and a base react. So let's go ahead and take a look at one example. The first example we're going to see is Na2CO3, sodium carbonate. Now, initially, when you look at this doesn't really look like a base or an acid. There's no H pluses, there's no OH minuses. I don't have a nitrogen from like that amine group that will accept a proton and then it acts as a base as well. So it's pretty tricky to see how this thing could be acidic or basic when you put it in solution. So the way we're going to analyze this is using two things. We're going to be taking a look at what conjugates are again. How are these ions in solution related to an acid or a base? How are they conjugates of those? And we're going to be looking at hydrolysis reactions to help us understand that. So a hydrolysis reaction is the reaction of water with something. And typically we're going to be meaning an ion. You could have hydrolysis reactions with other things, but we're going to be taking a look at the reaction of water with ions in solution. We saw before that the definition of the pH is related to the autoionization of water and how water can react with itself. Here, water is then going to be reacting with ions in solution. So let's go ahead and consider both of the ions in Na2CO3 to see how hydrolysis plays a role in making this compound either an acid or a base. So let's go ahead and take the CO3 first. If you take CO3 and react it with water, I could make kind of two predictions here. The first thing is that this thing doesn't have a proton, so it doesn't really have a way to donate a proton. It's negative 2 in fact, so it looks a lot more like something that's going to accept a proton because it has those extra electrons, that negative charge. And indeed, it is going to accept a proton. The other way we can think about it is we've always seen acids producing H plus and A minus in solution. So acids tend to produce conjugate bases that are negative or that are anions. So our anion here, number one here is our anion, it's going to act here as a base and it's going to accept a proton from our H2O here. And so we're going to write an equilibrium reaction where my CO3 2 minus accepts a proton from my water, forms HCO3 minus and OH minus. And so I can see here how CO3 2 minus is acting as a base because it goes ahead and produces OH minus ions in solution. So one thing we can note is that the anion in any ionic salt is always a conjugate base of an acid. Now something we should think about is how strong is that conjugate acid of this ionic base here that we've seen. So if you look at HCO3 minus, this is not one of our strong acids. Therefore, it is a weak acid. And we know weak acids exist in equilibrium, and they don't ionize very much at all. And so if I consider this equilibrium based on this equilibrium wouldn't lie completely to the left because it's not a strong acid or base. And so I will get some OH minus in solution. Therefore, I can conclude that because of the CO3 2 minus, there is going to be some OH minus in my final solution here. Let's go ahead and take a look at the sodium then. So the other ion associated with my Na2CO3, number 2, is sodium. Now, if the anion of my ionic salt is acting as the conjugate base of an acid, you can probably surmise that the cation is going to act as an acid then, and indeed it will. If it reacts with water, the hydrolysis reaction has sodium reacting with water to form NaOH, and then it looks like I'm going to go ahead and need an H plus here as well. Now, so you can write down that a cation is always going to be the conjugate acid of a base. Now, something to consider here is that this base that I formed here, NaOH, we know that's one of our strong bases. It's a group 1 metal hydroxide. And so because of that, this equilibrium is going to lie extremely to the left. In fact, we say strong bases always go to completion. And so this H plus concentration here, because of the Na plus, is going to be near zero. There's going to be no H plus formed by the hydrolysis of sodium in water because its conjugate is so strong. And so we're going to say this doesn't appreciably happen. Therefore, because ion 1 makes it slightly basic and ion 2 doesn't really do anything, we can conclude then that Na2CO3 is a basic salt. So what you should have seen now is that there are two ways to kind of analyze the acidity or basicity of a salt. You want to take a look and see what are the conjugates of the ions in that solution, consider their hydrolysis reactions and which way those equilibrium are going to lie, and once you've seen that, you can make a firm prediction about where that equilibrium will lie here. So what we're going to do now is just take a look at a few examples to make sure we firm up our predictions here. So our first prediction I want to make is what happens when I have something like NaCl. Well, if I have NaCl, I can probably see if my cation, the metal, comes from a base, it's always the conjugate acid of a base, that the conjugate from this one, from NaCl, is NaOH, which is strong. And for Cl minus, that's going to be coming from a strong acid, HCl, so strong base and strong acid. And so we can say that this is an example of strong with strong. And so if you have strong with strong, we've seen this kind of interplay that the stronger an acid or a base, the weaker its conjugate acid. So since you have a really strong base, we don't even say that its conjugate is even really an acid at all. It's so weak, it doesn't really act as an acid. So a strong base produces not an acid in solution, and so the Na plus isn't going to do anything. It's just a spectator here. Similarly, the strong acid is going to produce a conjugate that's so weak that it's not even really not a base. And so we can predict that the Cl minus is also not going to play a role here in this here, and thus we can predict NaCl would be neutral, which indeed that kind of fits with our confirmation. We know that salt is a neutral ion in solution. So anytime you have strong paired with strong, we're going to see a neutral solution for our NaCl. Up next, I'd like to take another example here. The first one I'd like to do here is now talking about what happens when I combine a weak acid and a strong base. Well, if I combine something that comes from a weak acid and a strong base, that might be something like NaNO2. The Na, like we saw up here, that's coming from NaOH, which is a strong base, which, like we said, will have no effect. It is not, the conjugate then, the Na plus, is not really an acid at all. And so the Na plus won't do anything in solution. But now I have this NO2. NO2 minus comes from HNO2, which is importantly not HNO3. HNO3 is nitric acid that's strong. This is HNO2, nitrous acid, and it is not a strong acid. It is weak. Therefore, because this is a weak acid, the conjugate of it, NO2, is a weak base. And so we would predict that because of that NO2 there, that this is a weakly basic solution, because the NO2 forms a base or an OH minus ion in solution because of its hydrolysis reaction. So one pattern you might start seeing is that if we combine a weak acid and a strong base, we're left with a salt that is slightly basic. You can think of it like that strong base is kind of overcoming that weak acid and leaving you with something that is slightly basic. Now the third example I'd take a look at is just the opposite. You could probably predict if we combine a strong acid with a weak base. Let's consider something like NH4 Cl, ammonium chloride. If you look at ammonium chloride, the acid NH4 plus, that comes from the weak base of ammonia, NH3. And since that's a weak base makes a weak acid conjugate. And so therefore, we would predict that NH4 is slightly acidic. Whereas the Cl minus, we've seen already, comes from HCl. That's strong. a strong acid, and therefore its conjugate is not a base at all. And so the Cl minus isn't going to play a role, and so we would predict now that this solution is slightly acidic because that strong acid kind of overcomes that weak base, produces a salt that is slightly acidic. Well, as you can imagine, there's one more case that we haven't seen, and of course it is the most difficult case. In number 4 here is we're going to consider what happens when you combine a weak acid with a weak base. Now, to do that, I want to consider a very particular example. We're going to take a look at ammonium nitrite, NH4, NO2. Now, our NH4+, we're going to consider the two ions that we have here. NH4+, it comes from the conjugate NH3, which we already know is a weak base. And then NO2- comes from HNO2, our nitrous acid, and we've already seen that is a weak acid. And so what's tricky here is that a weak base, NH3, when it forms a salt, will form a weakly acidic salt. The weak acid, HNO2, when it forms NO2-, will form a weakly basic salt. And so because of this, we would predict that the NH4 is an acid, and the NO2 is a base, and so we have no way to predict exactly just qualitatively which one of those is more acidic or more basic. And so here, what we need to start doing is actually analyzing the equilibrium reactions that we have going on here. So to analyze these equilibrium reactions, we're going to take a look at the hydrolysis reactions for both NH4+ and for NO2-. So our first one was NH4+, and NH4+ reacting with water would form NH3 and H+, like we said, being slightly acidic. And then number 2, that NO2- reacting with water would go between HNO2 and OH- being slightly basic. Now, when we consider these equilibrium reactions, these look exactly like the equilibrium constant expressions we've written before. For an acid here, we have the Ka of NH4 would be equal to NH3 times H+ divided by the concentration of NH4+. Similarly, for our second reaction, we have HNO2 times OH- divided by our NO2-. Now this one is not an acid dissociation constant because we're making a base. We call this Kb, our base dissociation constant. So we have both our acid and our base. Now like we saw at the beginning of the video, all we would need to do is know which one was stronger. Was the Ka of this one larger than the Kb of that one? And then we can evaluate the strength of our acid or base here. But we have one slight problem. If you look in your textbook on Appendix C.2, tables A and B, there's a list of the Kas and Kbs of common acids and bases. But if you look, they don't have NH4+ and NO2- because they are ions. The acids and bases they do list are things like these here. And so what we can look up is that NH3, the Ka of that base, sorry, Kb of that base, NH3, is 1.8 times 10 to the -5th. And then for HNO2, the Ka of that acid is 7.2 times 10 to the -4th. At this point, we have two options for analyzing this. We could make one argument just using these numbers, or we could look at this more quantitatively. Now, for that first part here, if we take a look at these two numbers, NH3 has 1.8 times to the -5th, and HNO2 is 7.2 times 10 to the -4th. That means that comparing their strength, HNO2 is a stronger acid than HNO3 is as being a base. So based on that, we've seen already that these strengths are inversely related. Because this one is stronger, it's going to lie more to the left than this one will. And so because of that, we might make the prediction based on this, that NH4 plus is stronger than NO2 minus. It's an inverse relationship. And indeed, if you made that prediction, you would say that this salt is slightly acidic, and you would be correct that because the NH4 plus is slightly stronger than the NO2 minus, it is going to be an acidic solution. But that might be a bit of a difficult thing for us to predict here, and we might want to look at this quantitatively. Now, the way we can look at this quantitatively is we have to know the relationship between Ka and Kb. And so what I want to do is take a look at the NH4 plus reaction real quick with water and see how I can relate it to NH3 here. So I already know NH4 plus reacts with water to form NH3 plus H plus, but I know instead the Kb of NH3. And the Kb of NH3 is going to describe the reaction of NH3 plus with water. And NH3 plus with water is going to go ahead and form NH4 plus OH minus. And then the Kb is going to be NH4 plus times OH minus divided by NH3. And so we can see that's a similar reaction to what we've seen up here. Now, in order to relate the Ka and the Kb, what I can do is I can go ahead and play a game by adding these two reactions together. If I add my NH4 reaction below, I get H2O and H2O there, NH3 plus H plus. And if I add those two reactions, I'm going to notice that I get things that cancel out on both sides. I'm going to cancel out an NH4 plus from these two sides and NH3 from these sides. And what I get when I'm left is H2O plus H2O. Let me put an addition sign there. Goes between H plus and OH minus. And of course, this reaction is described by the Ka that I don't know. Well, we've seen this reaction before. In fact, in this video, we know this reaction is the autoionization of water. And so we know that the K for that reaction is Kw. Now, we've seen already that if I have the equilibrium constants of two reactions added together to get a third, I can write a mathematical relationship between those. And so I can say that the Ka of this reaction here times the Kb is equal to Kw. This is an important statement. It helps us understand what's going on in these weak acid, weak base equilibria. This reaction tells me that the stronger the Ka for an acid, the weaker its conjugate base, because as I increase Ka, Kb must decrease for the conjugate in order to make Kw be the same, and vice versa. The weaker the Ka, the stronger the Kb. And so if we wanted, we could go ahead and calculate the Ka and Kb of NH3+. And if you'd like to do that, go ahead and give it a try, where you plug in the Kb of NH3 here, Kw is that 1 times 10 to the minus 14th, and solve for Ka. This Ka, of course, is going to be for the conjugate acid, NH4+. And if you do that, the Ka of NH4+, it looks like when you plug it into your calculator, ends up being 5.6 times 10 to the minus 10th. And for HNO2, sorry, not NHNO2, NO2 minus, the conjugate base of this, when you plug in the Ka and solve for Kb, I end up getting, looks like 1.4 times 10 to the minus 11th. So I've got minus 10 here and minus 11 here, and that confirms that original prediction that we had before, that NH4 plus is going to be stronger than NO2 minus. And think about this. When we said HNO2 is stronger than NH3, we just used the Ka and the Kb. And we used the fact that this equation implies an inverse relationship to say that because HNO2 is stronger, the base that it comes from, that NO2, must be weaker. And the NH3, because its Ka, or its Kb was a little low, the acid that it is a conjugate of is going to be a little stronger there. And so we would finally predict that this salt here, NH4NO2, will be acidic.